so-called higher order functions. So here is another example of a function. We want to find a block with a particular property. So we have been writing this function hasBlock, which checks whether a particular number is contained within a chain. But perhaps we want to have a slightly more interesting properties. Is there a block that is greater than 10? Or is there a block that has an even number? Or is there a block that has a number that is divisible by 7? Or something like that. In order to model all these properties, we can just choose a function and say if we have a function of type txs was just a synonym for integer to bool, then you can look at it as a quick way of defining some sort of property on integers, a test on integers. Given an integer, it says yes or no, right? And if we abstract our function over such a function, then we get what is called a higher order function. That is a function that is parameterized by another function. So hasBlockProp is yet another Haskell function definition, example of a Haskell function definition. It is very similar to the hasBlock function that we've seen before, but the difference is that rather than taking a concrete number here, a concrete value of txs, this first argument is actually another function of type txs to bool. You can think of this as a test or a property. So it takes this property, it takes a chain, and then it delivers a bool. And here we have to put these parentheses because the function arrow associates to the right. So if we wouldn't put the parentheses around these two, then it would be a function, a curried function that takes 3 arguments, a txs, a bool, and a chain. But if we put these parentheses around txs to bool, then this is a single argument that is of function type. Now again, we have 2 equations, one for the Genesis block and one for proper blocks. Again, if we ask whether there is a block with a particular property in a chain that doesn't have any proper blocks, then we always say false. But if we are in a proper block now, then we give C, the name C to the chain that we're extending and T to the integer that is in that block. And now we just call prop, which is a function from txs to bool on T. And T is of type txs or int. So prop applied to T will give us a Boolean that will just say this particular property we're interested in hold for that T or not. Before we were writing prop x equals T, where x was this argument that we were passing before in hasBlock. Now we're generalizing this is equal to something property to an arbitrary property. And now we can put in different properties. And here we get use of another common feature of functional languages, and Haskell in particular, but one that is so popular that by now it has infiltrated most of the programming languages world. So most languages these days actually support anonymous functions one way or the other. If you want to pass an argument to this hasBlockProp function, which is a function of type txs to bool, but you don't want to define a new function and give it a name, you can just define a function on the fly using a lambda expression. These are called lambda expressions in Haskell. And the way to read this one is, this is the function that takes an x and computes x greater than 10. So it tests whether a given x is greater than 10. And you can also read this as lambda x. The backslash is typically read as lambda, the Greek letter lambda x arrow, x greater 10. Okay, or the function that takes an x to x greater 10, whatever you prefer. So this tests whether there is any block within chain 2 that has a value that is greater than 10. And that is not the case because chain 2 contains 2 blocks, one being the number 2 and one being the number 4, neither of which are greater than 10, so the result of this is false. Even as a predefined function of type int to bool, so it can be used in this place, so it checks whether an integer is even. If we ask whether there is any even number in chain 2, then we get true, because both 2 and 4 are actually even. We can also get essentially back what we had before, an equality check, by saying, is there any element in the chain that is equal to 4, because one of the elements is 2 and the other is 4. This will also result in true, sorry. Right. In particular for operators, these sorts of simple applications of operators where one argument is specified and the other is essentially left unspecified is so common that Haskell has an additional syntactic shorthand for this and allows you to write within parentheses just an operator that is applied to one of its arguments, leaving the other one out. And that is a shorthand for such a lambda abstraction. So you can equally well write lambda x arrow x greater 10 or just greater 10 within parentheses. And that means the same thing. Is the thing greater than 10 or is the thing equal to 4? These are called operator sections. That is a convenience feature. So Lars was saying earlier, Haskell is a minimalistic language. That is only true in a particular interpretation of the sense. So the syntax is not very cluttered, right? There are lots of things that can be expressed with very few syntactic tokens. It is, however, not a language that is minimalistic in the sense that there is only one way to do everything. In fact, Haskell has many syntactic conveniences, and often there is more than one feature in the language that can express a certain concept. And this is one such example. And these features are often layered on top of each other, where you can say this operator section is a shorthand for a lambda abstraction, and the lambda abstraction is in a way a shorthand for just defining a function with a name, but it saves you from giving a name to this function. Okay. Here's another such example of just this sort of multiple ways of doing such a thing, just to give you a little bit of an outlook of how Haskell looks and how Haskell syntax can look like. So this upper style that I've just given before is the way that you would typically define has block prop, right? But if you would want to go back to simpler features of the language and have one construct to do everything, then you can say, so lambda abstractions are the most basic feature to introduce functions. And there is a construct in Haskell that's called case that is the most basic feature that does pattern matching. So you could express the same function has block prop in this style, where you say has block prop is a function that takes prop and chain as arguments, then does a pattern match on chain, distinguishes the two cases. If the chain is of shape Genesis block, it returns false. This case statement confusingly takes right arrows rather than equals symbols. So that is often confusing to beginners as well. And if the chain is of shape block CT, then the right-hand side from here is just taken. So that is just another style, right? We'll learn about more of these syntactic constructs over time. In the beginning, we're mostly, and also this is the normal style of writing functions by pattern matching and multiple equations. So this is what we're mostly using. But case statements are still useful, or case expressions are still useful if you sometimes want to do an ad hoc intermediate match. In the beginning, this will rarely arise, but it is it's good to know, right? It's not minimalistic in the sense that there is only one way of doing things. Okay. So we've seen three functions, all on chains: chain length, has block, and has block prop. And if you look at them, they're all functions over chains, and they're all having a similar shape, right? Each of these functions has two equations, one for Genesis block and one for block, right? And also each of these functions has a recursive call to the sort of initial parts of the chain that we're extending in the block. So here we're calling chain length C in the block case. Here we're calling has block on C in the has block case. And here we're calling has block prop on C in the block case. And this is not an accident, right? This is not just because these functions happen to be almost the same. This is because that is what the structure of chains is like. The way that we define chains in the beginning, I said that chains are a data type that have two different shapes, one being Genesis block, the other being block. And block, the block constructor, was mentioning a chain to be extended recursively, right? And you'll see that one of the natural properties that hold for Haskell programs is that functions follow the structure of the data that they operate on. Because the data type of chains has two constructors, and most of the functions on chains will have two equations, one for each of these constructors. And because the block constructor mentions chains recursively, most of the functions operating on chains will make a recursive call to that chain that occurs recursively in the block constructor. And this is a good thing to keep in mind, because it gives you a programming principle that arises from the data type definition. And I cannot emphasize this enough. This will be the main lesson, that if you learn this and nothing else during the first week of the course, that functions follow the structure of the data, and this is the guiding principle, then I'm already happy. Of course, I would be even happier if you learn more. But this is, if there's a single thing about basic Haskell programming that is most important, then it is this thing, this aspect of it. And we'll see this come back again and again for various different data types, that the natural way to define a function over the data type is to look at what is the definition of the data type, to split into multiple equations depending on how many different shapes, how many different data constructors the data type has, and to be recursive where the data type is recursive. And this is an example of this type-directed programming that Lars already mentioned, where if you look at the types and you're aware of the types, basically give you half of the program. They give you the structure of the program that you want to write. So this is, also think about this when you start looking at the first exercises. We'll get back to this and we'll repeat this and we'll do it in more detail again. Keep this in mind. Also, if you start writing your own first few Haskell functions, this is the basic structure that it always comes back to. Check if there are any questions. Quick questions. Which one is better in performance? Switch case or first one? These are, yeah, as Lars already answered. If you're wondering about these two, these are exactly the same in performance. So basic things like this, that they don't make a huge difference. If you would actually use a different algorithm and write things in a completely different style, then it might very well affect performance.
There's another question, what the double colon means.
Colon means is of type, right? So this is what comes back mostly in the type signatures. So is a way to introduce a type signature for a function. Has block prop in this case, is of type, and then this right-hand side. So this is the symbol that plays a big role in type signatures, but it is also the symbol that is used by GHCI to communicate the types of something to use. So we've seen this with the colon T. If I'm asking here, what is the type of, let me go to the other GHCI session. If I ask what is the type of chain 2, then it says chain 2 is of type chain, right? Or what is the type of not, for example, the function not, it is a type or a function of type bool to bool. And again, you'll see this double colon symbol come back there.
And in particular, it's not just functions, it's
not just functions, as you can see here. It is just every expression in Haskell has a type, regardless of whether it's a function or not. It just means is of type. So let's briefly look at type inference to start with. If you write a function definition like this, just to get a feel for what's the kind of thing that Haskell is doing, Haskell sees that you have equations here that have two things on the left-hand side, right? Two arguments and a result on the right-hand side. So from just that shape, Haskell can infer, even without you writing this optional type signature, even if you would omit it, it can infer that the type of this has block prop thing must be of this shape, something to something, because you have these two arguments here. Then what's the next thing that we could be doing? You could look at this false here, for example. False is a data constructor, actually, of the type Boolean. I can show this briefly. If you ask iBool, you'll get a lot of information here, some of which is not yet understandable to you, but in particular, it'll show you the actual data type definition for Booleans, and it'll show you that Boolean is a data type defined just similar to chains, right? Having two constructors, false and true, both without any arguments. So this is really just a type that has these two shapes, false and true, as you would expect a Boolean to be. No other structure, okay? So false is a data constructor for Booleans and is in particular of type Boolean. So just from the presence of bool here on the right-hand side, we can conclude that the result must be Boolean, right? And if we look at this here, Genesis block, it is a pattern as a constructor for the chain type, and similarly block CT is of type chain. So because these two things are of type chain, we know that the second argument must be of type chain, okay? And then, because of the block type, because the block is of type chain to TXS to chain, we know that this T here is of type TXS. And then if we look at T, it's being used as an argument to prop. And if TXS is being used as an argument to prop, and prop is the first argument of our function, then prop has to be a function that takes a TXS to something, right? And what does it take it to? The result of prop T is then used as the first argument to OR, and OR we've already seen as an operator of type Boolean to Boolean to Boolean. So the result of calling prop T must be bool. So just by looking at various pieces of the code and using information about the types that we already know, we can infer what the type of this must be, and then check that all the other occurrences are consistent with this. All right, so we, of course, then that GHC also does this, then looked at, okay, the second argument to the OR operator here has also to be of type Boolean, so this is a recursive call, so prop better be a function of TXS to bool again, which it is, and C better be a chain again, which it is, because block, the first argument to the block constructor is a chain. So this is roughly how type inference works. Of course, this is informal. In practice, there is a very mechanical, algorithmic process that Haskell programs run through that infer these types and check them. But you can do this yourself. And even though Haskell does it for you, still one of the things that make you successful and productive as a Haskell programmer is to become familiar enough with the Haskell type system that you do not have to rely on GHC for everything anymore, that you develop a feeling yourself for what is type correct and what is not type correct and how do things fit together, and do this kind of reasoning quickly in your mind as well. So that is a good exercise. But also, yeah, test yourself and then try :T and GHCI. Initially, you'll get lots of type signatures that don't make a lot of sense because of overloading and polymorphism that we're going to talk about, which we'll cover in a lot more detail later. But nevertheless, trying to test yourself and train yourself and build an intuition is key to becoming more proficient. Let's go to polymorphism, actually. So here is our chain data type again, as I've shown it in the very beginning. And I've also said that these are vastly simplified, and there are multiple things that is simplified about these with respect to proper blockchains, of course. But in particular, the most drastic simplification is probably that we said that like every block contains just an integer. Now we could say, okay, instead of containing just an integer, let's say it contains a list of transactions and then we define what a transaction is or something like that. But we could also just leave it open and say we can consider chains of various contents and decide use by use what kind of chains we want to consider. And this is something that is allowed in Haskell, and you can abstract from the type of transactions. You can have data types that are themselves parameterized over other types. So this is now no longer introducing just a chain data type, but it is introducing a chain of some transactions type. TXS is a type variable that can stand for any other type. In particular, it could stand for integer, but it could stand for something different. It could stand for Boolean, then you would have a chain that would contain truth values. But you can have a more complicated type, a data type that you define later that actually defines structure of transactions and metadata and so on and so forth. And then every block within the chain would still contain the same type, TXS. But for different uses of chain, we can now choose different instantiations of this type. And because chain is now a parameterized type, the recursive occurrence of chain here also takes this parameter. So the recursive occurrence of chain is another chain of the same TXS. And then the types of the constructors change and they become polymorphic, as it's called. They involve type variables. So Genesis block is now of type chain TXS. It can be an empty chain regardless of what the element type of those chains is. It doesn't have to be specified. It works for any chain. So this remains a variable saying that it's universally usable as the block of any chain for regardless of the element type. And block also becomes polymorphic, as it's called, by saying it extends a chain of some transaction type with a new transaction of the same type, and then builds a longer chain of this transaction type. But again, as the caller, whenever you call this, you can choose to instantiate this implicitly to chain of integers, to a chain of booleans, to a chain of something more complicated than that, right? And then if we just basically leave our function definitions unchanged and let GHC re-infer the types of our functions, we'll see that the functions that we've written, they also become polymorphic, because our chain length function never looks at the elements of the chain, so we can compute the length of a chain regardless of what the transactions that are stored in the chain are. We can always compute the length because it's just looking at the structure. And hasBlockProp actually works on chains of an arbitrary transaction type as long as the property is compatible. The property that we're checking for is compatible with that transaction type. So these two things have to match, but we don't care really whether they're integer or Boolean or something else. Right? Again, we'll talk about polymorphism in a lot more detail later on, but you'll see these types that involve type variables a lot, also in predefined functions. Many functions in Haskell are polymorphic. They work whenever you see a type variable occurring in a type, it works for any instantiation of that type. By the way, I haven't said this, but I should. How do you recognize type variables? Haskell has relatively strong conventions when it comes to whether identifiers start with uppercase or lowercase letters. So as you've already seen, normal identifiers, they always start with a lowercase letter. Data constructors, these are the things that make up the shape of data types, they always start with an uppercase letter. And then on the type level, you have also two different things. Data types themselves, like chain or bool or int, they always start with an uppercase letter. And anything that starts with a lowercase letter is a variable. Whether you call this chain TXS or chain A or chain foo, as long as it's a lowercase a and a lowercase, it doesn't matter. That is a variable. But if a variable occurs multiple times within the same type signature, it means it must be instantiated to the same type. Okay, so let me reiterate once more. Polymorphism is one of these features that we'll talk about a lot later. Right? For now, it's mostly to make you familiar with that this concept exists, that it allows you to write functions that work across a whole lot of different data types using just a single piece of code. But we'll look at like how this works in more detail later and what the pitfalls are and so on and so forth. Another big thing is overloading. So if we look at this hasBlock function that we've written before, and if we now look at it from the perspective of our generalized chain type, where we leave the transactions open, I said the length function doesn't care about the elements at all, but our hasBlock function does care about the elements because it does something with the t, namely it checks whether the t is equal to the x. Right? It runs this equality function, this equality test. And now the question is, what is the type of the equality test? And the equality test in Haskell works for many different data types, but not for all. So there are some types where you can check whether two values are equal, and there are other types where you cannot check whether two values are equal. And for example, for integers and for booleans, you very easily can, but for example, for functions, you cannot, right? Because there are multiple reasons for this, but first and foremost, Haskell is a compiled language. At compile time, we only really have the code of functions. Even if you had exactly the same function to start out with, like depending on compiler settings, it might be compiled to different code. So it would be really difficult to decide whether two functions are equal. Also, if you look at it mathematically, then it doesn't really make sense to consider functions only equal if they have exactly the same definition. So you would probably want to consider them equal if they behave the same on the same arguments. And that is a theoretically undecidable problem, whether two functions behave the same on all arguments, even if they're defined in different ways. So functions don't support equality tests, right? But integers and booleans are. So some types do, other types don't. And the way this is written in Haskell is by means of a type class. So this becomes more interesting to read now. This equals test has the type a to bool. So you can start by just reading the part after the double arrow, a to bool, which looks like in a polymorphic type. You have two things of the same type, and then ultimately you say yes or no. But now you cannot choose any instantiation for a, but you must choose an instantiation for a type that is a member of the equality class, EQ. That you can think of EQA as being a constraint, capturing all the types that support this equality test. And that is what's called a type class constraint. And again, the way to read this is, or I typically read this as the equality test has the type a to bool. I start here, and then I say as long as a is an instance of equality. So it's best to separate out this double arrow part and see it as an additional constraint on what choices you can make for a. If there's no constraint here, you can instantiate a to any Haskell type whatsoever. If there is a constraint, you can instantiate it to any Haskell type that satisfies these constraints. Okay. So another thing that is already worth pointing out is that the chain data type that we've introduced is very similar to a built-in Haskell data type of lists. Just that chains are sequences of equally typed things that grow to the right, and lists are sequences of things that grow to the left, and they have built-in syntax that makes them slightly, ultimately more convenient to use perhaps, but in the beginning slightly more confusing because they don't behave exactly the same syntactically as other data types you would define yourself. So the list data type is also parameterized by its element type and is written with square brackets and an element type in the middle. So this is the type of lists of A, lists of elements of type A. And then there is a constructor that corresponds to our Genesis block constructor that represents an empty list that is written just square bracket open, square bracket close. That is an empty list. And then there's an operator that's called cons for constructor, because in a way this is sort of the, like when the theory of data types was, like of algebraic data types was first developed, people were fascinated by lists, and lists were the thing that most people were using all the time. And because the interesting constructor for lists, the list constructor is just called cons as a short form for constructor. And so cons takes a single element, which is the first element of the list, and the tail of an already existing list, and plugs them together and forms a new list that is like the combination of this first element and the rest. And just like you can build arbitrarily long chains by taking the Genesis block and calling block repeatedly, you can build arbitrarily long lists by taking the empty list and consing elements to its beginning one by one. And then you have parametric polymorphism in these lists as well. And similarly to how you can write a chain like this by nested application of a block constructor, you can write a list of integers, but it grows to the left, right? You always prepend elements, so the empty list, and then you cons 1 on it, and then you cons 2 on it. So that's a list that first contains 2, and then 1, and then nothing further. And there is a lot of syntactic sugar for lists. You can write a list using this very explicit form, or you can recognize that the list constructor is right associative and omit the parentheses, or you can write lists just using square brackets and the elements separated by commas. And that is why lists are so much more convenient and why lists are used a lot, because they have this convenient syntax. But it also makes it a little bit harder to understand that whenever you actually write 2,1 within square brackets, what Haskell really sees internally is 2 cons 1 cons the empty list. So something that is built from data constructors applied to their arguments, just in the way that we've seen for chains. There are multiple ways of dealing with strings in libraries and more efficient ways, but the first and foremost one that is exposed to you immediately is a viewpoint where a string is just a list of characters. So there are character literals in Haskell, single character literals, which you write between quotes. So this is the character X and the character Y. This always just be a single character. And you can write X cons Y cons the empty list to denote a string that contains X and then Y. And you can also write that like this, or you can write it like this. This is an extra syntax available for strings, where if you have a string literal, you can surround it in double quotes. So single quotes, always a single character, double quotes, a sequence of characters, a list of characters, a string. But these are interchangeable. Type classes, like I said, the equality test, there are lots of them, right? And this is also why I'm introducing them now, because if you start looking at lots of predefined functions in Haskell, things that you have available right from the start, you get a lot of type signatures that look like this. So length is a function that doesn't tell you it's taking a list of A's to an integer. It's telling you, oh, it's taking a T of A to an integer, where T is an instance of the foldable class. And then it goes on. If you ask what is lm, it's a function that takes an A and a T of A to a bool. And there's a sort of element check. And again, you can think of T of A as a list, and of lm being a little bit similar to our hasBlock function for blocks. But it has these additional constraints on the variables. A must be an instance of EQ, and a lot of the functions that are predefined, very versatile, and they can be used on a lot of different things. So it is helpful to be able to read these kinds of functions. And if you have multiple constraints, as you see here, like for lm, then the syntax looks like this. You still have a single double arrow, and the constraints will all be grouped together and listed between parentheses. So these are just multiple constraints that have to be fulfilled for these type constructors here. But that's the level of detail I'll leave it at. Let's see, perhaps, is there a list? Yeah, there is a list of, just to give you a little bit of an intuition. Type classes in Haskell is not so much like data types as something that is very much domain specific. When you define a new program or write a new program, you very often start out with the data types, and you start defining new data types and making domain specific data types and defining functions over them. Type classes, you mostly use the existing ones. It's much rarer to define your own new type classes. That is just because type classes incorporate very ubiquitous interfaces that are usable in a lot of different settings. And most of these interfaces already exist or are already known. Okay, so it is somewhat less likely that you invent a new one that is really useful in a wide setting. So most of the times you define a lot of new data types in your code, but you're making them instances of already existing type classes. But you can define your own type classes as well. But in the beginning, the most likely type classes that you'll be confronted with are these: EQ for types that support equality, ORD for types that support ordering, num for types that are numeric, fractional for types that are numeric and support fractions, show for types that can be turned into a string representation, that have a string representation, read for types that can be parsed back from a string representation, enum for types that can be enumerated, bounded for types that have the smallest and the largest value, and foldable, that's the one that we've seen just now, for container types. The most prominent instance of foldable is lists. So for starters, whenever you see foldable, you can think list, right? Yeah, here are a number of other examples just of functions that elem I've already shown. Any is a function that checks whether there is any element in there that has a particular property. So any is very similar to our has block prop function. elem is very similar to our has block function. And then you can specialize these to various concrete types. Here are a number of other predefined functions that will certainly come back, in particular on lists, very useful functions on lists. You can reverse a list. Reverse is taking a list of A's to a list of A's. Just turn the order around. We can also try this. Reverse of 1, 2, 3 is giving 3, 2, 1. And it doesn't matter what's contained in the list. So that's why the type of reverse is list of A to list of A. So I could equally well take a list of Booleans and reverse that. The function reverse is also polymorphic and works for any element type. Plus is an operator that appends to lists. So again, I can take 1, 2, 3 plus 4, 5, 6, and I get a single list that has 1, 2, 3, 4, 5, 6. Filter is a higher order function that takes such a property as we've seen and takes a list and retains only the elements that satisfy the property. Map is a function that takes a function from A to B and a list of A's and applies that function to every element in the list. So map is incredibly useful, and you probably know this from other contexts or other languages because it is a function that these days exists in a lot of settings. So I can use map to add 1 to every element in a list, or multiply every element by 2, or if I have a list of lists, something like this, 7, 8, 9, I can reverse every one of the inner lists by mapping a reverse over this, and then I get 3, 2, 1, 6, 5, 4, and 9, 8, 7. Or I can reverse the outer list as well if I want. I can write interesting programs as well.
Maybe you should have picked elements of different length, otherwise it looks as if.
I could. I'm just very fond of 3. But I can certainly do the same thing with lists of different length. I can have length on this, so length, then I get 3, 3, 5. That changes the type of the original list of resulting one as just a list of integers.
Right.
Okay, and there are very generic functions that are useful sometimes as special cases and special situations. Like there's the identity function that just returns whatever you feed it to, and it works on any type. There is a constant function that takes 2 arguments and always returns its first argument. So this is often used as a partial application. So for example, I can also map const 3 over this function, and then I get, like, each of these lists is applied to the constant 3 function, but the constant 3 function always returns 3, so I get 3 times 3. One funny way of implementing length would be mapping const 1 over the list and then summing up all the resulting ones. That would also give you back the length of a list. That is perhaps not the way that you would normally define length, but it works. These are some operators just to make you familiar with the types of things that you'll get. Plus is an operator that takes 2 A's that must be numeric and gives you back an A. Numeric types that are multiple, in particular integers and doubles, but also rationals and other. There is division that only works on fractional numbers on types like double or rational, but not on integers. And there is comparison that has this OR constraint that tests whether something is less than or equal than something else. And there is also a function called show that turns everything that is in the show class into a string. This is one of the most common errors you'll get in GHCI. If you type in a function on its own and just hit return, you'll get an error from show, saying no instance for show for function types, essentially, because function types also cannot be shown. And GHC, what it does whenever you type something in, it tries to evaluate it, and then it uses the show function to produce the string representation that is actually printed back to you. And if something does not have a show instance, then it cannot be printed back to you. And so that is something that is interesting to have seen. So this doesn't actually mean that anything is wrong with this expression. It just means that it's not of a type that can be printed. And you can see that there is this implicit call to print that is shown here in the error message. One important thing that you'll see very soon, very quickly, because we are going to start working with our own data types also right at the beginning with this chain data type. If you define a new data type in Haskell, it starts out without any operations on it. Everything you have to define yourself. The only thing you have available is pattern matching, as we've seen in our functions on the chain data type. It is not an instance of any existing type classes. And making it an instance of some type classes is possible in Haskell, but it can be tedious. For example, writing an equality function on chains is an interesting exercise for beginners, but it is ultimately getting boring rather soon. You just want structural comparison all the way through. Two chains are equal if they look exactly the same, right? Similarly, turning something into a string representation, you can say, if you get a Genesis block, I want to return the string representation of Genesis block. Again, that gets boring rather soon. So for some of these basic classes, GHC can be instructed to give you the obvious definition automatically. And you can use this deriving construct to say, give me the obvious definition of equality, the obvious definition of show, and the obvious definition of foldable for this type. And then you'll just have instances available. So that saves you some work. You could always expand this and say explicitly what you mean, but it is a good opportunity if you define new data types to encourage you even more to define your own data types. Because if you would have to define everything by hand, then you might not end up defining your own data types and use existing ones, and then everything would be less descriptive and less domain specific. And Haskell wants to encourage you to define your own data types. Therefore, this deriving construct is a nice compromise. And you'll see that in the exercises that we'll use that a lot in the beginning. If we confront you with new data types, we'll often derive EQ and show at least to be able to compare things for equality and to print things back to the screen. And that's very useful. But sometimes there will be exercises that basically go along the lines to let you re-implement some of these as well. And then we'll deliberately omit some of these deriving clauses. In Haskell, whenever I have a function, it's a pure function in the mathematical sense. That means the function result depends exactly on the function input and on nothing else. If I call a function on an input, then it has a result. If I call a function somewhere else in the program on the same input, it has the same result. Right? It does not matter in particular how often I call the function, which weekday it is, whether I have a network connection or not. These kind of things, they do not matter. If it depends on the inputs of the function and on nothing else. That is another way to phrase this is functions have no side effects. Right? The only thing that goes into computing the result of a function is its input. Right? How do you express side effects then? Because obviously we do want side effecting programs. We do want functions that communicate over the network. We do not want functions that write things to disk or read things from the keyboard or print nice graphics to the screen or depend on random numbers or access the system time or all these sorts of things. The trick is that these functions are distinguished by the type system. We have, in particular, we have this IO type, which is a parameterized type that indicates computations that may have side effects. And so you have to distinguish between a function f that is of type int to int, and this is a completely deterministic, pure, as it's called, function, where the output integer depends only on the input integer and nothing else. And you have functions like this one, which go from int to IO int. And here the output type is not an integer, but it is an IO of integer. And a way to look at this intuitively is that the result is not a value, it is an action, right? So if is a function, G is a function, yet you can feed an integer, but the result is an action. And the action, the nature of the action is always the same, right? But the execution of the action can lead to different integers, right? So it could be, G could be an operation that takes an integer and then reads that many characters from a network socket, or that many bytes from a network socket, and then does some computations with them and produces the resulting integer. And of course, depending on what it reads, there may be multiple different integers every time you execute that function. But that's why the result is not an integer, the result is an IO integer. As I said before, we'll discuss this in much more detail later, but the point for the time being is that every function that performs side effects in Haskell, be it accessing the disk, accessing the network, using random numbers, all these kind of things, has such an IO marker or a variant of it in its result type. And if it does not, if a function looks just like this, then you can rely on it not having side effects. And actually this latter thing is why this distinction is really useful. So marking all the side effects is useful because then the absence of the marker is telling you that you can rely on that function being completely deterministic. And deterministic functions that are not having side effects are much more well behaved. It does not matter, for example, how often and when you're executing them, whether you are executing them in parallel, whether you change their order, whether you speculatively evaluate them, and so on, whether you send them to a different machine and evaluate them over there. It should always have the same result. So much more opportunity for optimization, much more opportunity for testing. So these pure functions are much more well behaved. Normally, in most languages, you have to make this pessimistic assumption that side effects are everywhere because you don't have this explicit distinction. If you have to make a pessimistic assumptions, you can never reliably benefit from the knowledge that something is free of side effects. Haskell basically encourages you to follow a programming style where the distinction is rather clear. And it may at first seem that it's not useful because in the end, everything will have side effects. But that is not actually quite true. And we'll see the moment we introduce IO into our programs, we'll see that with a little bit of discipline, you actually have quite a lot, surprisingly a lot of code that is not relying on side effects directly. And this is an interesting feature. So just to give you an example, read file is a function that takes a file path, which is just a string, so a name of a file, and then accesses that file on disk and gives you back the contents of that file. But of course, this is a side effect, so this is not a function that goes from file path to string, but from file path to IO string. Right? And then you cannot use your normal operations on IO. You have to use different operations because IO is more tricky. You have to be more careful about what happens in which order. And you cannot just apply length to read file or file because length expects a string or a container, but IO of string is not such a container, it's an IO action. And you need to use some different syntax here. And then in order to compute the length of the file, the result will still have type IO int, because in order to compute the length of a file, you'll still have to access the disk. Right? Once you are in IO, you'll always stay in IO. And there are these like fancy operators that I'm just showing them now that can be used to combine IO actions in all sorts of funny ways. But the key thing about this IO marker, about these explicit effects, is that they're reliable to quite some extent. So results that depend on effects always have an IO marker in their types. And it's very difficult to lie about this. It is possible, but it is very difficult. And in practice, it is difficult enough so that you can, in practice, rely on it. If functions have non-IO types, you can rely on them being side effect free. But the rest I've basically already explained. Okay. Now, the very last point is lazy evaluation. And here I just want to give you one more example of a function definition. So this is a function build that takes an integer to a chain of integers. Right? So it's a function that takes an integer as an argument and produces a chain as an output. And the idea is it builds a long chain. It builds a chain that is as many blocks long as the integer you give it, and it puts some numbers into the blocks. So if the integer is less than or equal to 0, the integer that we pass it, we'll return the genesis block. And otherwise, we'll produce a block. We'll recursively call build on n-1, and we'll put the current value of n into that block. All right. So let me see if I have this here. Build 5. Okay, so this is giving me numbered constructors here because I have multiple variations of the chain data type in the same source file, but whenever it says block 4 and genesis block 4, you can just read block and genesis block. And then it has 5 blocks, and the blocks are numbered 1 up to 5. So that is what the function is doing. Here is another example for just 2 blocks. If I call build of a very, very large number, and then call the length of this, then it will ultimately print the same number. But if I make the number large enough, it will take quite a long time, because we will build this long chain, and then length will traverse it again in order to compute what the length of that chain is. Okay, so that will take a while. But what do you think happens if I build this very long chain, and I ask whether there is an even block in there? Does anybody have an idea? Will this also take very long? Will this be very fast? Or will this perhaps cause an error? Or will this take forever? It outputs true, yeah, but how soon? What do you think? Is it faster than length of builds of 10 million? After I build 1 million blocks, yeah, that's not true. It'll output true almost immediately. And why is this? Why is the output here nearly immediate? Let's look at the equational reasoning again, right, that I've shown in order to think about Haskell programs. If we have this expression, we need to look at what this build of 10 million. And if we expand the equation for build of 10 million, we get this if-then-else expression, right? Just replacing the left-hand side with the right-hand side. Now, if you look at this condition here, is 10 million less than or equal to 0? It is not, right? This is false. And therefore, the else branch will be taken here. So we can make this simplification. Actually, it's done in one more step. So first, we simplify this expression to false, and then we simplify the if-then-else. And then we have has block prop even of block, build of 10 million minus 1, and 10 million. All right. So at this point, we have 2 options. Right? We can continue evaluating build, and that is what most other languages would do. And that is what's called eager evaluation. We can continue evaluating build because it's the argument to our function call, and most other languages first fully evaluate function arguments before they enter the functions. Haskell is always trying to evaluate the outermost call if it's possible, and that is what's called lazy evaluation. So we have a call of has block prop even to block build 10 million minus 1, 10 million here. And if we look at the equations for has block prop, it has 2 equations, one for genesis block and one for block, and the one for block matches right here. And we can replace the left-hand side with the right-hand side. And then if we have this, we get to this. And then we have even of 10 million or has block prop even of build of 10 million minus 1. And now the outermost function call is the OR. And in order to reduce the OR, we have to at least look at what is the left argument of the OR. But even of 10 million is true, right? That's what we assume if even is defined sensibly. And now OR is again an operator that is actually defined using pattern matching. But interestingly, if you know that the first argument of OR is true, right, then regardless of what the second argument evaluates to, the result is always true. OR says like the one or the other thing has to be true. If one of them is already true, then the whole thing is definitely true. And OR is defined in such a way that it does not need to compute its second argument in order to produce true in this result. And because Haskell tries to evaluate the outermost expression first, it can say true at this point. So it never builds the whole chain. So this is what's called lazy evaluation, right? Outermost expression first, as soon as it's possible to reduce it. And that in particular means if you have expensive computations and arguments to functions, they will only be computed if they are actually needed in order to produce the result, only at the moment where they're actually needed. And that has a lot of implications. It has both positive and negative implications. The positive implications are that you potentially save quite a lot of work, that you more easily can decompose a lot of problems in a lot of different steps and do not have to be afraid that decomposing will introduce additional costs. That's actually the most significant benefit of lazy evaluation, that it encourages writing things in modular style as composition of multiple passes without incurring additional costs in performing this decomposition. But the disadvantage is that it becomes a little bit harder to reason about the actual complexity of your program, because sometimes things look expensive and you have to look very carefully in order to decide whether they're actually going to be computed or not. And sometimes that leads to surprises in the runtime behavior or the performance of your program, and not always positive ones. This is a positive surprise, right? There may be situations where you're negatively surprised, and we'll certainly see one or two of these cases later on. All right, so lazy evaluation, to summarize, means that in terms of looking at it syntactically, always the outermost, and if there are multiple outermost calls, the leftmost of them call is reduced first. Expressions are only evaluated when needed. And it also means that we can potentially work with infinite values. So we can write down a list of infinitely many elements, and then if you only look at an initial part of that list, then the rest of these elements are never going to be computed. You can write repeat one, for example, that gives you an infinite list of ones, and it'll just go on and on printing this list until I interrupt this. If I say I want to only have the first 100 elements of this list, I can compute this without ever building the infinite list of ones. So this is having a lot of implications. This is it, summary, what we've seen. So perhaps classifying once more like being able to define higher order functions and having algebraic data types and pattern matching. This is basically something that all functional languages share, or as far as data types and pattern matching are concerned, at least statically typed functional languages share. Then type classes are rather unique to Haskell. Other languages have sometimes other features to compensate for this. So Haskell does not have a very advanced module system. I haven't even mentioned it. Other languages like OCaml or F# or ML, this family of languages has a much more sophisticated module system instead, basically to compensate for the absence of type classes. But explicit effects and lazy evaluation are really almost unique to Haskell. Most other languages that have this at least take some inspiration from Haskell. There are languages like Idris or Agda that are inspired by Haskell that have this, or PureScript for web programming has explicit effects but not lazy evaluation. Yeah, most other languages that have one of these two are at least probably inspired to some extent by Haskell. So this was a long first overview, but we're going to look at exercises.
Chào các bạn. Mọi người đều biết là mình chỉ dùng phân tích kỹ thuật để giao dịch và đầu tư. Cụ thể là mình dùng Python. Chính vì dùng phân tích kỹ thuật cho nên là mình không đọc tin tức về tài chính bao giờ cả, để không bị FOMO và bị đi theo cái tâm lý của đám đông. Có thể bạn không đồng ý hoàn toàn với mình, nhưng mà đó là cách mà mình vẫn sử dụng từ ngày xưa đến bây giờ. Và chính vì thế mà dù mình sống ở Hà Nội, nhưng mà mình mù tịt thông tin, chả biết tin tức gì về tài chính cả. Nên là mình không biết là có cái làn sóng nhà đầu tư F0 ở thị trường chứng khoán, mới đây là thị trường bất động sản. Đến khi mà cái chỗ mình hay ngồi làm việc, chả là mình hay ngồi làm việc ở quán cà phê, bắt đầu thấy càng ngày càng đông những người ngồi cạnh bàn tán về thị trường, mua cái gì, bán cái gì, mua mã cổ phiếu này,